Okay, next, spherical coordinates. So spherical coordinates are a little bit different, and they take a little bit of getting used to. And there are some messy details that we're going to avoid for just right now. So think about it this way. If I take any point in 3 space, x, y, z, instead of thinking it in terms of its rectangular coordinates, those, I'm going to think about theta. So theta is exactly the same as it was in polar coordinates. Okay, this r would be the one in polar coordinates, but we're not going to think about that one. Instead, we're going to define another angle, phi. And phi is going to be the angle from the positive z-axis. So we have two angles, one from the positive x-axis, one from the positive z-axis. And then, as in polar coordinates, I'm going to measure the distance away from the origin, but this time it goes out into 3 space. This distance is called rho. Okay, so you do some messy trigonometry, and you end up with these translations between rectangular and spherical coordinates. So this x-coordinate is given by rho sine phi cosine theta, and similarly, y is given by rho sine phi cosine theta, so notice these only change in the theta values. And then this distance z above the xy plane is given by rho cosine phi. Okay, we're in spherical coordinates, so applying Pythagorean's theorem twice, we get the relationship that the distance from the origin, rho squared, is equal to x squared plus y squared plus z squared. As with cylindrical coordinates, a box is no longer a box exactly, and this box has a little bit more curviness to it, in fact, than in cylindrical coordinates. It's curvy in two directions. But again, with some patience and some trigonometry, we can find that the dimensions of the box are rho delta phi, rho sine phi delta theta, and delta theta. And multiplying those three things together, we get the replacement for dv. Again, this is replacing dv equals dx, dy, dz, the rectangular or Cartesian coordinate dv. Here we're going to replace it with this piece. Again, it's a little bit messier, but it's always exactly the same. There's always a rho squared sine phi piece, and then the d rho, d phi, d theta I can put in any order that I choose. Okay, so let's try an example. So here's the example we'll try. We're going to try to evaluate the integral 1 over this mess over the region W. Now this is a region in 3 space, and that region is the bottom half of a sphere of radius 5 centered at the origin. So first notice that x squared plus y squared plus z squared, that's exactly rho squared, and rho squared to the 1/2 is rho. So right away, this turns into a triple integral of w over 1 over rho. There should be a dv in there, sorry, dv. Okay, so the issue here is simply to determine what those limits of integration are. And then we're going to integrate 1 over rho dv. Now dv, remember, had a rho squared sine phi piece in there, so I'm going to put that in before I forget. Okay, now let's think about what this region W is. This region W is simply the bottom half of a sphere, so it's the sphere and it's of radius 5. So it's a sphere below the xy plane. And then there's that circle, which is the cross-section in the xy plane. Okay, so I get to pick the order of d rho, d phi, d theta. So let's start with the easiest one, perhaps is d rho. The rho values simply go from the origin, and it's a sphere, so no matter what direction I go, I always go out 5. So I go from 0 to 5. D theta, remember that's the angle that lives in the xy plane, and I go all the way around. So that goes from 0 to 2 pi. And then finally there's the new one. So phi, remember, phi is the angle from the positive z-axis. So as phi sweeps around, I don't hit the region that I'm interested in until phi gets to pi over 2. So this region is going to start at pi over 2, and then it's perhaps a little bit tricky where we want to stop. We want to stop here at pi. Why? Because if I went further, I would count some regions twice. Theta has gone all the way around, so for a theta value, say back there in the second or third quadrant, I'm going to get a phi that goes from pi over 2 to pi. So in order to not double count, I want to simply go up to pi. Okay, so I think I forgot this last d phi. Okay, so I'll copy this onto the next slide and then we'll finish this integral. Okay, so this first integration is with respect to phi. So an integral of sine phi is minus cosine phi, and I'm going to go ahead and simplify that while I'm at it. So I'm going to get rho with a negative cosine phi. We're going to evaluate that from pi over 2 to pi, and then finish the other two integrals when we're done with that. Okay, so cosine of pi is minus 1, and cosine of pi over 2 is 0. So on the inside, the minus 1 and minus rho gives me rho minus the lower limit of integration, which is 0. So it's pretty nice. We just get a rho. And then we're going to integrate with respect to theta from 0 to 2 pi. And then with respect to rho from 0 to 5. So integrating with respect to theta, we get rho theta from 0 to 2 pi. Plug in the 2 pi, and I get 2 pi rho minus 0 at the lower limit. So now we're at 2 pi rho. Integrate that from 0 to 5 d rho. So an antiderivative with respect to rho is pi rho squared from 0 to 5. And so finally we get 25 pi. And that's the value of the integral we started with.